Continuing with example 6 on page 9, the series in part C is in summation notation, but we're going to do this the same sort of way. First of all, we need to recognize that we are dealing with an infinite geometric series, okay? The infinite part is pretty clear because we're summing to infinity, okay? And then if you look at the expression that we're summing up, it has the format a number times r to the nth power. All right, so here the r value or the common ratio is what is being raised to the power. So r is 5/9 here. Okay, the summation, the index of summation is j here, so that is in the exponent. So that's a big clue that this is geometric whenever your index of summation is in the power or exponent. So that's our n value here, and then the number a that we're multiplying by out front is just 1. Okay, so this is definitely a geometric series. You could, if you didn't see it from this perspective, you could start writing out terms and then look at how you go from one term to the next and realize that this is indeed geometric with a common ratio of 5/9. Okay, now since the r value is 5/9, that means that the absolute value of r is the absolute value of 5/9, which is indeed just 5/9. That is less than 1, so this infinite geometric series will converge. Okay, to figure out what this series converges to, we have to plug into our formula, okay, the formula for S infinity. This formula holds only for geometric series, infinite geometric series, okay? So it is going to converge to A1 divided by 1 minus R. Okay, we already know r, so I'm going to go ahead and plug that in. The denominator here is going to be 1 minus 5/9. Okay, we need to get a1, the first term of the series. Okay, when you are working with summation notation, you might think that you can look at it and tell what the first term is. I highly recommend just taking a few extra seconds and computing it, because it really depends on what your exponent is, whether it's j or j minus 1 or something else. It can really affect your first term. Okay, so take an extra couple of seconds and figure it out. Okay, so if I want the first term here, that means I need to plug in j equals 1 to my expression. Okay, so a1 is going to be 5/9 raised to the first power. Okay, everywhere I see a j, replace it with 1. Okay, so the first term here is just going to be 5/9. All right, so if I return to my formula and plug this in, I'm going to get 5/9 for a1. That's going to be divided by 1 minus 5/9. Okay, so this is going to be 5/9 over 4/9. Okay, so we're going to leave the top fraction alone, change division to multiplication, flip the bottom fraction. The 9's cancel since there's 1 in the top, 1 in the bottom. This series is going to converge to 5/4. Okay, meaning if you were to write out all the terms of this infinite geometric series and add them all up, the sum is going to be 5/4. Okay, all right, let's try another one. Okay, again, we have our geometric series written in summation notation. Okay, again, how do you recognize this as geometric? It is in the format a times r to the n minus 1 power. Okay, the index of summation here is I. You can call it I or n or whatever. Okay, but you're seeing that index of summation up here in the power. Okay, all right, so when you look at this, okay, whatever is being raised to the power here is going to be your common ratio. Okay, so that is 1/4. Remember, the 3 is on the outside. It's multiplied on the outside. It's the 1/4 being raised to the power. That is going to be your common ratio. Okay, if you take its absolute value, that's going to be the absolute value of 1/4. Okay, that's going to be positive 1/4, which is less than 1. So we will get convergence here. Okay, anytime you're doing one of these and you have an absolute value of r that's bigger than 1, you can just automatically write down diverges. Can't add it up. Okay, all right, so to add this guy up, we're going to plug into S infinity is equal to a1 over 1 minus r. We know the R value is 1/4, so I can pop that in. Again, I don't want to just eyeball this and say what the first term is. I'm going to calculate it out to the side here. If I'm looking for the first term, that means I need I to be 1. Okay, so replace in your expression I equals 1. Okay, so we're going to get 3 times 1/4 raised to the 1 minus 1 power. That's going to be 3 times 1/4 to the 0 power. Anything to the 0 power is 1. So 1/4 raised to the 0 power is 1. So it's going to be 3 times 1. So the first term here is 3. Okay. All right. So if I plug that in for A1, okay, this is what we're going to get. Okay. So this is going to be 3 over 3/4. So this will be 3 over 1 times 4/3. The 3's will cancel. Okay. And so this series adds up or converges to 4. Okay, again, if we wrote out all the terms, can't write them all out because there's infinitely many, but if you started writing terms out and tried to add them up on the calculator, the sum should be tending to 4. All right, next, okay, here's another summation. Okay, again, it's an infinite sum. When we look at it, we see a number times r to the n minus 1 power. Again, we have an index of summation of I. Okay, the clue here that this is geometric, it fits this bill. Your index of summation is in the power. Okay, all right, so to start here, your R value is what's being raised to the power. Okay, so we have a negative R value here, meaning if you did start writing out the terms of this series, you would have alternating signs. Okay, but this still converges because if we take the absolute value of the common ratio here, this is going to be the absolute value of negative 1/3, which is positive 1/3. That is less than 1. So we again have a series that converges. Okay, to figure out what it converges to, we apply S infinity, that formula. Okay, so A1 over 1 minus R. Okay, I'm going to go ahead and plug in the R value since I know it. Be careful here because the R value is negative. The denominator is going to be 1 minus a negative 1/3. Okay, the top, we're going to go out to the side and compute A1. Okay, for the first term, that means I needs to be 1. We're going to have to plug in an I value of 1. Okay, so we're going to get 2/5. That's just multiplied out front. Negative 1/3 is what's being raised to the power. We're going to pop in 1 for I. So it's going to be, the power is going to be 1 minus 1, which is the 0th power. So we have this. Okay, so again, 2/5 is just hanging out front. This is going to be 2/5 times negative 1/3 to the 0 power is 1. So the first term is 2/5. Okay. All right. So we go plug this in. Okay. So we have 2/5 over 1 plus 1/3. Okay. So it's going to be 2/5 over 1 plus 1/3. Okay. This is going to be 2/5 over 4/3. Okay. And then this is going to be 2/5 times 3/4. Okay, this is going to be 6 over 20, and this reduces to 3 over 10. Okay, this series converges to 3/10. Okay, again, if you started writing out terms and you tried to add them up on the calculator, you of course cannot add infinitely many. But if you tried to add up as many as you could, you should be seeing a sum that's approaching 0.3. Okay. All right. Last one we'll try here. Hopefully you've got the hang of it now, but this one's a little bit different. Okay. Here we are, of course, summing to infinity. We have another infinite sum, but this one might be a little difficult in terms of recognizing this as geometric. We have a negative power. Okay, the index of summation here is k. The 10 is being raised to the negative k power. Okay, so, is this geometric or is it something else? Well, let's look at it. Okay, what's going on here? I'm going to just start writing out the first few terms so you can see what's happening. If k equals 1, the first term here is going to be 10 to the negative 1 power. And so remember how you eliminate a negative exponent? You're going to do 1 over the something, but then change the sign of the exponent. So this is actually going to be 1/10, okay, is the first term. And then if I bump up my counting number to the next term to get the second term in the sequence or series, I'm going to plug in -2, okay, because I'm just replacing k with 2. This is going to be 1 over 10 to the positive 2 power. So this is going to be 1 over 100. Okay, this was 1/10. I'll do one more so you can see what's going on. If we pop in k equals 3, our third term is going to be 10 to the negative 3 power, which is 1 over 10 cubed, which is 1 over 1,000. Okay, so this series here is really 1/10 plus 1 over 100 plus 1 over 1,000, and so on. Okay, so basically to go from one term to the next, how do we go from 1/10 to 1 over 100? We multiply by 1 over 10. 1/10 times 1/10 gives you 1 over 100. Okay, and then to go from 1 over 100 to 1 over 1,000, you again multiply by 1/10. Okay, if I do 1 over 100 times 1/10, that's going to give me 1 over 1,000. Okay, so this is a geometric series. Okay, your R value is 1/10. Okay, so another way that you could see this, okay, without actually writing the terms of the sequence out like we just did, okay, I'm going to come over here because I'm running out of room. Okay, if you think about this 10 to the negative k, okay, we could rewrite it in the expression. Okay, if this is 10 to the negative k, this is the same thing as 1 over 10 to the positive k power. Okay, so we could look at it this way. Okay, and we could go a step further here. Okay, this is the same thing as the sum from k equals 1 to infinity of the quantity 1/10 raised to the k power. Okay, so like if I have a fraction raised to a power, I can take the numerator and raise it to that power, in the denominator and raise it to that power. Okay, 1 to any power is 1. Okay, so this is another way right here that you can write the summation. Okay, and if it's written in this format, okay, you can more clearly see that it fits the bill of some number times r to the nth power. Okay, it's geometric. The a value would be 1 here. The r value, the common ratio, would be 1/10. Okay, so these are the two different ways you can see that this is a geometric series with an r value of 1/10. Okay, since the r value has an absolute value that is less than 1, okay, we will get convergence here. So I'm just jotting this down, that the absolute value of r is positive 1/10, which is less than 1. We're going to converge here. Okay, and that makes sense. When we started writing out the terms are quite small to begin with. It's like 0.1 plus 0.01 plus 0.001 and so on. Okay, the terms are getting smaller and smaller as we go on. We expect convergence. Okay, it will converge to a1 divided by 1 minus r. Okay, we know the first term is 1/10. We've already computed it. Okay, the r value is also 1/10. Okay, so this is going to be 1/10 over 9/10. Okay, so this is going to be 1/10 times 10 over 1, or sorry, 10 over 9. The 10s will cancel. Okay, and we get that this particular series converges to 1/9. Okay, which is a tiny number. Okay, that's expected based on what we've seen the series do. Okay, all right. Okay, so this was just quite a few examples of geometric series. Okay, how you can use that formula for S infinity to compute the sum of an infinite geometric series. Okay, the key to doing this is remembering that the only way an infinite geometric series can converge is if the absolute value of r is less than 1. Okay, if you have an absolute value of r that's bigger than 1, automatically your series diverges.